Hello, everyone, and thanks for joining us for another edition of National Museum of Industrial History's Virtual Museum Talks. Today we'll be talking about the iconic blast furnaces at Bethlehem Steel. If you've ever been to Bethlehem or been to the museum, you've obviously seen those outside. And our historian today, Mike Piersa, is going to be telling you a little bit about how they worked and what they were used for and how they use them to make metal. Also want to take a little bit of time to talk about some of our other upcoming talks. We have a kind of companion talk to this one coming up this Wednesday, which will be about the blowing engines that powered the blast furnaces. And also coming up this Friday, we're going to be talking with Richard Hall about John Roebling. We had a talk a little bit ago with Erica Wagner about his son, Washington Roebling. So we're going to have Richard come on and talk about his father and his role in the Brooklyn Bridge and how it was built. We also have some kids programming that's going to be launching this week. Our first program is coming up tomorrow, and we also have a live program that will be taking place on Thursday. And you can check out more information about those talks and events either here on our Facebook page or at our website at nmih.org. And if you're tuning in right now, you obviously are not paying anything for this talk. And if you've been tuning in to some of our other talks, we've had, I think this is our 14th or 15th program that we've done for free for everyone at home. And we've brought people on from all over the world, all over the country, and we've had tens of thousands of people watching in our videos, and we want to thank everyone who's been able to join us. And if you're able to please support the museum right now. Obviously, we're closed, but there's a couple different ways that you can help support us at home. One of those is buying a museum membership. Another is just making a general donation to the museum. Or if you're using Amazon to buy products at your house, please use Amazon Smile and select the National Museum of Industrial History as your charity of choice, and part of your purchase will go towards us. You can find out more ways that you can help us out right now and more information about those ways at our website at nmih.org, or if you're watching live here, I'll be posting the link in the Facebook comments in a little bit. But I want to thank again Mike Piersa, who's a museum's historian, for joining us. Mike's a graduate of both Moravian and Lehigh University. He's been with the museum in some capacity for over 17 years now. He's done a ton of work with the museum's collections. If you've ever been inside the museum and seen the way everything's set up and the interpretation behind what's in there, Mike has had an instrumental role in doing all of that with his time with the museum. And he's going to talk about one of the most iconic things in Bethlehem, the blast furnaces today. If you guys have any questions while you're watching today, please post them in the comments. We'll be trying to answer them live or towards the end of the talk. And we encourage some interaction there. So without further ado, I will pass it over to Mike.
Thank you very much. I'm going to do a screen transfer right now to begin my slideshow. And hopefully it'll go smoothly and we'll be up and running momentarily. So the first picture you're going to see here is looks like a pile of dirt. But when you talk about the very, very early blast furnaces, before even the ones you have here in Bethlehem, this is one of the ways you had to start out. And this is important to understand before we get into what's in Bethlehem, because this sets the stage for all of the furnaces that came later. This thing that looks like a pile of dirt is actually charcoal burn. There's a big mound of wood underneath there, covered in soil, and the wood's set afire. This doesn't completely burn. You want it just enough to burn a little bit of it, and then drive off the impurities in the upper wood. And eventually, after several days, you get charred wood, where the non-carbon based materials have been primarily burned off of it. Not really burned off, but baked off. And you're left with charcoal. Not the same type of charcoal we have like in barbecue grills today, like the briquettes. That's a more modern product. But basically wood that's had the vast majority of the impurities theoretically removed and is a good source of carbon. Carbon is really what you want, because when you combine that carbon with iron ore, you have a chemical reaction that, along with heat, takes place to remove the oxygen from the iron ore and leaves you with theoretically pure iron, but it's really iron that's mixed in with about 4% carbon, and it comes out of the blast furnaces. So this is what a typical early furnace would have looked like. This one's on the more ornate end. This is out in Ohio, but these were scattered all over Pennsylvania, Northeast, and many other areas of the country. They're typically built into hillsides. Let's see, bridge on the right, so you can take raw materials in and charge alternate layers of charcoal, iron ore, and limestone. The pyramid-shaped opening at the bottom is, we'll explain all this more in detail later, but where your tuer goes, that's the pipe that puts the air into the furnace. The air provides the oxygen for the chemical reaction to occur, so there's actually multiple reactions that take place inside the furnace. You have your oxygen from the air combining with carbon from the charcoal or anthracite coal or coke, whatever you're using, depending on the time frame, and that leaves you with carbon monoxide gas. Between the heat and the carbon monoxide gas, the carbon monoxide joins with the oxygen in the iron ore and creates carbon dioxide gas, which goes out of the furnace. And there's still some leftover carbon monoxide that gets handled by, in some of our modern furnaces, the piping network, or in this case, just goes out into the atmosphere and the air and creates a really interesting flame as it's ignited at nighttime. But the bottom line is, once you remove that oxygen from the iron ore, you're left with basically metallic iron plus whatever carbon mixed in there. Now, when you look at this, you'll see that this furnace is surrounded by trees. And notice that they're not really thick, like 2 or 3 feet in diameter. They're all fairly small trees. And this would have been the case even 100 years ago, because these charcoal furnaces required a tremendous amount of woodland around them that they needed to harvest the wood to make the charcoal. So you would have a furnace, and then several miles around it, you'd have almost barren stretches of landscape because you had to take down all these trees and convert them into charcoal. So it really was not a sustainable practice. Martha Capel Fox covered this very well in her lecture, but in this part of the country where we had ready access to anthracite coal, anthracite is a very, very carbon-rich form of coal, and it eventually proved that it was ideal for putting into blast furnaces. But what they figured out very early on was that you can't take a traditional charcoal furnace like you saw there and put anthracite into it. Those furnaces were just blown. That means had air put into them that was just regular cold air from the atmosphere. And if anybody here has ever tried to light anthracite in a stove, it's a struggle. Anthracite is a really peculiar fuel. It was nicknamed stone coal. Early attempts to burn it were so unsuccessful that they dumped it as ground covering for sidewalks because they couldn't get it to ignite. But for anthracite iron purposes, where you want to use the coal as a source of carbon for smelting iron, it was eventually discovered that if you heat the air up before it goes into the furnace, it was several hundred degrees, that was the temperature of the air necessary to get the anthracite coal to actually burn and do its job in the chemical reaction. So that finally happened in the Lehigh Valley in 1840, and on the 4th of July, 1840, at the Crane Iron Works in Catasauqua, they were able to smelt iron with anthracite coal, and that's when the Lehigh Valley transformed from the handful of charcoal furnaces to what would become in a couple of decades the leader in the country for iron production because of anthracite coal. And of course, ready access to iron ore from our own area and neighboring states. So the first anthracite furnaces were built of stone. This is an example of one at Hopewell Furnace, built in the 1850s. About half to 2/3 of the furnace eventually was done away with. So what we're seeing is actually inside the furnace now. You see the outside, then the pathway that the air would have taken to the inner portion of the furnace, the stack with the Bosch at the lower bottom of it. And then it rises up, and you can see where it's disappeared there. So you can see that semicircular form that would have extended upward and been a true stack that the furnace was made with. But what I can show you here with this furnace that's been partially demolished is the actual iron. This is called a salamander. This is what's left over when you take a blast furnace out of production. The furnace is not actually tapped, which is what they call the process of removing the iron, like tapping a keg. You tap the iron out of it. It's not actually done at the very lowest level of the furnace, so there's usually a couple of feet or more of actual liquid iron beneath that. And when the furnace is taken out of service, you have this big chunk of iron left over. In some places, they might try to drill into it and tap it out, but more often than not, especially in the early years, they just abandoned it in place. And sometimes guys would go back in later and try to blast it out and use it. But you can still drive around like Hewmore Park in Easton, and you can still spot these salamanders occasionally, because and they're often all that stuff of blast furnace that was long gone. So Bethlehem Iron Company was innovative from the very start. They never had stone blast furnaces, even though they're in common use in this region when the company began operations. This is the oldest image I'm aware of showing an actual blast furnace in Bethlehem. It's the small structure, relatively speaking, on the left with a pipe coming out of it diagonally. This shows the furnace and the plant in the process of construction, as it appeared in 1862 when there was a flood on the Lehigh River, which, to say the least, slowed things down. We can get an idea of what this early Bethlehem furnace looked like. It was actually an iron shell made of boilerplate, lined with refractory bricks on the inside. And we'll see it later on, but that pipe is actually a pipe that took gases off of the furnace. Because iron works were very aware that when they had an open top furnace and gas was going on in the air, they were literally letting money evaporate into the atmosphere. So Bethlehem Iron Company, this is a whole other lecture about how they expanded, but they had their first furnace go online in 1863. In 1867, they built a second furnace. And then the progression is kind of surprising after that. Their third furnace wasn't actually in Blast Furnace Row that we know today. It was actually the Northampton furnace, which they purchased from another company, along with 80 acres of land. And that furnace was located to the east end of number 2 machine shop, where that building currently stands, or just west of the Wind Creek shopping mall. That furnace went online in 1868 and ran until, we believe, 1884. So Bethlehem Iron Company actually had furnaces in multiple locations. They built a fourth furnace in 1874, but this one wasn't built strictly to produce iron like the other ones did. It produced a special grade of iron known as Spiegeleisen, which is actually 15% manganese. And this really shocked me, where they got the ore from. They imported it from an area near Palomares, Spain. Came all the way over the ocean to Bethlehem. But this was a really, really tiny furnace. It only made 35 tons of iron a week. And they used it because they needed that manganese content to use with the Bessemer converter to make steel. Manganese helped remove phosphorus, silica, and sulfur, and therefore produce a much higher quality of steel. This picture here, I believe, shows primarily furnaces number 5 and 6. Those were built in the 1870s by John Fritz. And this is a good time to move on to see a little bit more detailed drawing of what those furnaces look like, because up close, they're a little bit different than what you see here in the painting. This is a photograph of those furnaces. They're about 70 feet tall on the inside. And you'll notice that unlike those early ironworks where you had a bridge from the side of a hill to charge the furnaces, Bethlehem Iron Company was built on flat ground, and they used pneumatic-powered elevators to raise wheelbarrows full of material to the top of the furnace. And then there's these little short bridges that connect the elevator towers, which are the square-shaped shafts, to the round pieces, which are the actual furnaces. You'll see a cupola at the top of them with a stack coming out of it. That's where the men would actually work and charge material into the furnaces. Despite their proximity to the heat and everything, there weren't that many accidents, but they did happen. There was a case where the furnace did what's called a slip, and that's where the material inside kind of builds up like a bridge, and then it collapses. And then as it collapses, flames shoot out of the furnace. It can really do some major damage and kill people. That happened in the 19th century and happened again in the 20th century. And it's a risk that's associated with blast furnaces. So here's a drawing from the National Canal Museum archives that gives you a little bit of a sense of what's going on inside these furnaces. Again, these were steel furnaces. This one here looks like an early one where it's just boilerplate riveted together. We'll see John Fritz's variation of that in a little while. But you can see the refractory brick lining it. Up at the very top, you have that bridge to the elevator tower where men would use wheelbarrows to charge the raw material in. You'll notice that the material doesn't go straight down the sack of the furnace. It hits this thing that looks like a bell. And that's exactly what the blast furnace workers called it, bell. What it did was it sealed up the furnace. Because remember, all of that carbon monoxide gas it was creating, carbon monoxide is flammable when you have enough of it and the right mixture with air. So what these iron companies did was they took a pipe off of the furnace, piped this carbon monoxide gas down to the surface, and they actually used it in stoves. So we talked before about how anthracite needed to be we talked before about how anthracite required a preheated blast of air. Well, they would use the carbon monoxide gas to actually be ignited, form a flame, and heat up the air through pipes that were going through stoves to warm up the air that was going inside the furnace. So to help keep that gas in, they have this bell system. So the bell would seal up the furnace and direct that gas down to those stoves where it could be burned. It could also be burned in boilers to raise steam to run steam engines. And of course, you still have to feed raw material into the blast furnaces. So what they would do is on this bridge, they have a cylinder that goes up and down. As that cylinder goes up, it pivots this walking beam. And then that rod above the bell goes down and the bell actually descends. So you would fill up around the bell with your raw material, your anthracite coal, your limestone, your iron ore, and then you would quickly drop the bell. The material would fall down around it, lift the bell back up again. That would seal the furnace off, and you'd have a minimal amount of gas escaping into the atmosphere. Another view of the plant, 1880s or 90s. And this is a good image to show how the plant is actually laid out. So we'll see if we can zoom in here. So if you look really closely in the center of the screen, you'll see a line that, actually several lines. Those are railroad tracks from the Lehigh Valley Railroad. That's what's First Street today. That's the street that you walk in on if you're going to the Levitt Pavilion. It's the street right in front of the blast furnaces, but that used to be a mainline railroad track there. And you'll look above that, slightly to the right in the image, you'll see the sign that says Engine House. We're going to be discussing that building on Wednesday. And above that is the stock house. That's where the raw materials for the furnaces came in. So the raw materials, before they got to that elevator shaft, had to be delivered somehow. And they actually had a giant stone building. A fraction of it is still intact today as the Bethlehem Visitor Center. It used to extend on hundreds of feet to the east. And it had a twin-track railroad trestle 12 feet high inside of it. They would come in with railroad cars, unload them, and then men would manually load the wheelbarrows up, put them into these elevators right on the top of the furnace, and charge the furnaces. The furnaces are hard to see, but they make these little fingers that come off of the building known as the stock house here. And attached to the furnaces are these sheds known as cast houses. We'll see images to those a little bit later on. And then railroad tracks that connect the cast houses down to other operations of the plant. What's interesting is how they dealt with the Lehigh Valley Railroad. Having trains cross over at grade, especially in an industrial operation in the mainline railroad, isn't the best scenario. So they actually dug a tunnel and used a tunnel below the Lehigh Valley Railroad to get their iron from the blast furnaces to the steel mill, which in those days was the Bessemer steel mill, as the iron foundry building. Sorry for the slow moving pace here. So this image here shows those 1870s furnaces. You can see one furnace on the left, a smokestack in the middle, and then this would have been a mirror image repeated on the right-hand side with the other furnace, which would have been number 5. So when you look at this image, you're seeing several things. The building with a triangular roof facing us is a cast house. You see that big pipe coming down. That's the downcomer that takes the carbon monoxide gas out of the furnace and directs it towards boilers and stoves. These stoves don't look like traditional stoves like you see in your house. What they have inside them are about a number of tubes about 20 feet tall, 8 inches in diameter on the inside, made of cast iron. And the blowing engines, which we'll discuss on Wednesday, pump air through these stoves. It gets heated up by the flame, and the preheated air then enters into the furnace. And we'll see that a little bit further on, how it actually makes its entrance underneath all of this heavy burden of iron ore, coal, and limestone. But as we look at this furnace, it has a very different construction from the rest of the earlier furnaces, and even from the modern furnaces today. This is what's known as crinoline construction. Those of you who studied 19th century women's fashion would know it comes from, not that I have, but it comes from the steel framework that was used to make these big skirts that some women used to wear back then. So when it came time to design the furnaces, they took their name from that. So it has these wrought iron hoops that encircle it, then these vertical bars that go skyward, and they're all riveted together. And there's openings like maybe 16 inches by 24 or so inches in between these iron bands and these vertical pieces. And there's little holes inside there. And you can actually use those holes to check out the furnace and how it's doing. If it got a hot spot, you might see that furnace behave a little bit differently. And then you could actually go in that crinoline construction, those hoops, secure yourself to it, and then do repairs to the furnace if you had to. This was a very interesting design pioneered by John Fritz in the 1870s here at Bethlehem. These furnaces are long gone today. They're about 70 feet tall on the inside, and they ran into the early 20th century. Just trying to change my image here. It'll move eventually. Really sorry about this. I think the computer's kind of freezing right now. See if I can try something else to get to the image I want. This might work. Okay, so once the iron came out of those furnaces, it had there are different ways of handling it. In the very early years, they would pour it out into a bed of sand, and this is a practice that survived well into the 20th century in some what they call merchant iron furnaces, like Sloss furnaces in Alabama. But anyways, this bed of sand had troughs cut into it, and then these troughs had runners going off of it, and these little, they look like fingers on a comb coming off. And when this was filled with hot metal glowing orange, it looked like piglets suckling a sow, so they called it pig iron. And that's how the local baseball team got their name. Okay, I'm just going to have to keep on going back to my reference images. But here's an actual photograph showing one of those more modern furnaces. I believe this one was out in Chicago, where the sand bed extended out. You can see the bed is actually sloping. That way you take advantage of gravity to let the iron flow. And Bethlehem Steel did this for a while, but by the 20th century, they were starting to invest in what was known as a pig casting machine. So they'd actually take molten iron, pour it into railroad cars or ladles, and then they would actually take that iron to these machines that had these molds that would have liquid iron poured into it. It'd be like a conveyor belt type of system. Some were circular, some were linear, but the iron would fill these molds, solidify, and then it would dump out into a pile, and then they would take it to foundries or whatever other end users were going to be handling the iron after that. So this is just another image of showing how that iron got stacked up, reclaimed, and moved around. This was taken at the Lackawanna plant with a steam-powered crane with an electromagnet, lifting up those pieces of pig iron. So Bethlehem Iron Company operated with those elevators and wheelbarrows into the early 20th century, but the competition was actually beginning to outpace them. In the 1890s, Andrew Carnegie helped spur what was called the Duquesne Revolution in blast furnaces. So what his company did out in the Pittsburgh area, they had a blast furnace and steel mill plant at Duquesne, Pennsylvania, along the Monongahela River, and they were looking for ways to, as usual, save money. So what they started doing was they invented a way to get raw materials to the top of the furnace without using elevators and wheelbarrows. Instead, you can see these structures, one in the middle of the picture, painted white, and one to the left, kind of elevated with peaked roofs. Those are actually hoist houses that house hoisting machines that draw in wire ropes that pull up skip cars up an inclined railroad to the very top of the furnace up there. Bethlehem, we'll go into more details about how those work, but this essentially automated the system and reduced your costs by a great deal. And other things that were associated with it was to fill up those skip cars. You had a trestle, which we see today in Bethlehem as a Hoover Mason trestle, more enhanced dust collection system, larger furnaces, and you can see in the picture, if I can zoom in here, I guess it's not working, but you can see 1, 2, 3, 4, 5 ladle cars that the liquid iron would actually be poured into, and then those liquid iron-filled railroad cars would transport the iron to the steelmaking furnaces. So this drawing shows the system a little bit better, and we'll be going through this in more detail with actual photographs. But you come in on this railroad trestle, and you have ore and limestone, at least in the case of Bethlehem Steel here in Bethlehem, PA, on the south side, closest to ArtsQuest. Then on the north side, closest to the furnaces, you have another set of bins devoted to coke. Coke is something that they started using in the 1870s and found strong use in the early 20th century for like basically running strictly on coke at that point. And coke is bituminous coal that's been baked to remove the impurities, so you're left with a very high concentration of carbon, very little other elements inside the product. Coke is also more porous than anthracite coal, so if you looked at those anthracite coal pictures, it was kind of shiny and dense, but coke almost looks like lava rock. It has a lot of holes in it, so when you're blowing air into the furnace, it can burn better, it can release the carbon into the rest of the furnace for the chemical reaction to occur. It's also very strong. Anthracite coal tended to shear away and break, but coke would actually hold up this very, very heavy load above it. So you can see the alternating layers of coke, ore, and limestone in the furnaces, and then there's also temperature markings here. It might be 400 degrees near the top of the furnace, but you're looking at 3,000 degrees by the time that hot air, which itself could be well over 1,000 degrees, comes into the furnace, and molten slag pours out. Slag is less dense than iron, so it floats on top, and it's poured out through what they call the monkey notch. And then iron at the very lowest point, and that goes into the hot metal cars. And again, we'll see more of this in detail as we move through the tour. This is just a overhead map image showing how the plant started evolving. If we go back here, you can see the original stockhouse by 1907, 1910 era. They were beginning to tear that down and replace it with a Hoover Mason trestle. And we'll see more materially just why that thing represented such a leap in efficiency and what the competition was doing that required them to make that move. You also notice that those old furnaces were getting torn down, but there's one little circle above kind of like the middle right of the image. Unfortunately, I don't have a laser pointer like I would have in person or a mouse I can show this to you with, so hopefully you can find it on the image here. But there's one little circle, and that's a hot blast stove from the original #2 furnace. That stove was added in 1904, and it stuck around well into the 20th century. When you look at the next image, that stove is still there, and 4 more have been added, and a furnace has been built. It's on the site of the old #2 furnace. The old furnaces, by and large, kept their locations and gave them over to the new modern furnaces that you see here today. So A furnace was built in 1915, remodeled in 1950. So there's actually 3 generations of furnaces that are on the site. You'll see B rising to the left of it. But as we start seeing these furnaces go up, it's a good time to see what else we found in the archives. And this is a very humanizing and fascinating letter. I'm hoping you guys can read it. But it really answers some questions and breaks some assumptions we have. I don't know about you, but when you imagine heavy work like blast furnaces, you assume it would be people who just came over from Europe, young guys working. But this rather humorous letter from one of the superintendent of the blast furnaces, dated 1929, is talking about the labor getting on the furnaces, and it turns out the youngest worker was 52 years of age, and it reiterates something that I've heard from people who work with blast furnaces even to this very day. You kind of grow attached to them. They become part of your identity, part of your family. Even when you have the chance to retire, you really don't want to do it. You want to just keep on working with them. So he says it's a funny thing about blast furnaces. You become so attached to them. The only way you can get these old birds to quit is to hit them on the head. And then they look across the river to the old Niskey Hill Cemetery and think the happy hunting ground isn't far away. And if you add more labor-saving devices like one-man tops, automatic heat control, you might have to, well, you can read the rest of the letter on your own here. But that's what they were joking about in 1929 when they were discussing who actually worked on these furnaces. So now I want to move over and show you a shot of what the competition was doing. This is Lackawanna Iron and Steel Company, later purchased by Bethlehem Steel. They actually moved their plant from Scranton, Pennsylvania to the Buffalo area and built a plant right on the Great Lakes. So if you think about that Duquesne Revolution and how raw material handling was transformed from being manual to automatic, when you look at these plants on the Great Lakes, you can see a ship channel coming in. The ships go right into dock. This is a view from one of the ships. And you remember that ore bridge that's here in Bethlehem in front of One Creek Casino? Well, they had ore bridges in those plants too, but instead of picking up ore after it had been deposited by train cars, these ore bridges went right in, and they had Hewlett unloaders and other forms of machinery dump the ore right into that ore pile, and then it went into the furnaces. So right there, you had a tremendous cost advantage over the Bethlehem plant, which required about a 60-mile rail journey before you even got the raw material in from ships. And those ships often came from overseas. So here's another view. Again, this is a competition to help frame what's going on here in Bethlehem. It makes a little bit more sense where you can see how it evolved in other locations. So again, you have the ship channel, ore yard, and your blast furnaces. Bing, bam, boom. It's a nice, easy, very economical process. But because Bethlehem is really a Civil War era plant that just kept expanding and expanding, they had to figure out how do you make this system work and make it pay compared to these other plants that have those inherent natural advantages. So Bethlehem Steel developed the ore yard. It was located on what they called the ore farm, which was originally a limestone quarry. This is where the casino is located at today, because this was the really only good source of open ground close to the blast furnaces. If you wanted to build any closer, you'd have to tear down the machine shop or buy up homes and businesses. So this was the next best place that was available. So they established the ore yard here. They have a broad gauge railway running. It went to a sintering plant, which we'll explain momentarily. And then finally, about half a mile or so down the road to the blast furnaces. And that's the Hoover Mason trestle that we all know today. So it took this Midwestern technology and Western Pennsylvania technology and brought it back to Bethlehem and made it fit into this old plant to really give it new life. If it wasn't for a technology like this plant might have died in the early 1900s, like most of the other facilities in this area did. So there's actually a great book, a blast furnace manual published in the 1950s that I got these images from. This shows the ore bridge, over 500 feet long. It had a bucket on it that would deposit or pick up iron ore as needed, load it into a transfer car. This is a drawing of one that's a little faded, but you can see there's railroad wheels on the bottom and this inclined hopper that allowed iron ore to be dumped out of it in one direction. And this is a view inside that ore yard in later years. I mean, this place was huge. These guys were down there with bulldozers, moving things around. You can see the bucket on the right that held 15 tons of iron ore. And then this illustration shows how the ore was loaded onto those cars, and they were taken to either the blast furnaces or the sintering plant. The sintering plant is important to talk about here because remember we talked about how all of that carbon monoxide came off of the furnaces and those pipes. Those pipes also delivered a lot of dust from the furnaces. So that dust was actually collected and recycled through a machine in the sintering plant, where it's combined with coke dust and intense heat and a downdraft. And basically, for our purposes, you can describe it as being baked into a peanut brittle-like substance that could be broken apart and fit as chunks into the blast furnaces. Blast furnaces really don't like dust, but if material comes in lumps or chunks or pellets, they're okay with that. So this machine reformulated that dust into a usable material. The broad gauge transfer cars you can still see on the Hoover Mason trestle today. 7-foot 10.5-inch gauge hauled the raw material to the blast furnaces, except for the coke, which came in by standard gauge train from the coke works a few miles away. And then they dumped into bins. Now this is something you really can't see today. This is under the trestle. This was taken about 10 or so years ago. You can see overhead bins and then these rotating drums. These drums were connected to a line shaft, electrically motor driven, and they spun around as needed to help the material descend out of the bins and into scale cars. This is one of several scale cars that are still locked down there today. This was built by Atlas Car and Equipment in Cleveland, Ohio. And its sole job was to run in this little short railway underneath the Hoover Mason trestle. They call them scale cars because they actually have scales on them. And they're hopper cars too. So you would fill the bins up on these cars with raw materials from the trestle overhead. You would weigh it out on the scale. When you got to the right point, you would close the bin, and then you would move this car, which is electrically powered, kind of like a subway car, to the skip pit. And the skips, these breakers were taken to Carey furnaces in Pittsburgh, would lower down into this pit, be filled with raw material, and then go up to the top of the furnace. The skips were controlled by an electrically operated hoisting machine. It's a single drum hoist with a drum divided on the left side and the right side. And as one wire rope played out, the other would wind in. So it also helped keep the cars balanced out. So one car was at the top, one car was at the bottom, and they would meet in the middle. This is a view looking from the top down. And this really gives you a good sense of how the system worked. The cables pulled the cars up to the top, and then one set of wheels would actually ride on these funny shaped rails to the top, and that would allow the car to automatically dump and fall into the hopper you see below. And those arms and pins there are what actually move the bell up and down. So it's just like that early furnace. We saw the drawing of the bell, but in modern furnaces, there are two bells, or at least 20th century furnaces. So looking, this was from Carey furnaces in Pittsburgh. You can look down, you can see a bell. You can see how it's in the silo-shaped area, so the raw material falls down around it. You can still see there's some debris built up around it. Then it would drop down. The material would fall into the actual furnace and begin the process of smelting. This is what it looks like in between looking at the smaller bell. There's a small bell and the large bell. They form an airlock. So a very, very small amount of gas actually ends up escaping. And this would go up and down, and the material would fall down, and the joint it's opened up between that cylinder and the bell-shaped piece there. In Bethlehem, the bells were operated by pneumatic cylinders off of the blast gas, which was powered by the blowing engine. So there's just a big piston inside there, goes up and down, and operates that bell. You can see a picture of one under construction here. They actually cast them out of steel here in Bethlehem plant. They used steel because you could actually weld to them and build them up as they got worn out, and then machine them down to like new again. This is a view inside one of those more modern furnaces. You can see it has these legs that hold up the actual stack, and then there's these little fingers that come out in here. The temperatures are so intense that actually, the furnaces themselves have to be water cooled. This is a drawing showing what those coolers look like. They're made of copper. They have passages in there so the water can circulate through them. And then they're tied together inside the furnaces with these hoses, so the water keeps on circulating through these cooling plates and keeps the furnace from overheating. Now, the job that is required to actually keep these furnaces hot falls with the stoves and the stove tenders. So in the early days, we had cast iron pipes that were heated by flame. What they discovered was a much more efficient and more economical method was to use regenerative stoves. These were stoves that are steel shelled on the outside, but full of refractory bricks on the inside. This is a drawing of the stoves by A furnace. And you can see that they're full of refractory brick, but the brick is arranged so that before you start blowing air through them, you actually blow hot air with the gas flame. And this gas flame warms up the refractory brick to well over 1,000 degrees. It depends on the stove and the furnace exactly how hot it gets. And the heated air goes up, down, and then back up out the smokestack. Then you reverse that airflow with your cold air coming in from the blowing engines. And this is after, of course, you've turned off the gas and the bricks are preheated. They regenerate the heat that they've, I might be messing up the terms, but basically take these hot bricks and you blow the cold air over them. As the cold air passes over these bricks, it emerges from the bottom of the stove, nice and hot and ready to go into the blast furnace at 1,500, 1,000, 1,500 degrees, somewhere in that ballpark. They also had a mixing valve past the stove so you could mix in cold air so you could get that temperature to just the right piece that you want. Now, one thing to note is that you only need one stove at a time to actually provide hot air. But because you can only have one stove pumping hot air and the other one being warmed up, you'd actually rotate between the stoves. So you'd have usually a minimum of 3 stoves. One would be warming up with gas being burned inside of it. The other one would have the cold air going through and being heated by the pre-warmed bricks. And then the other one would be in a reserve in case you had some sort of issue. And some furnaces had up to 5 stoves. This is an example of one of the burners. You can see an electric motor, air intake, fuel would come up from the bottom, ignite, and really put a tremendous amount of heat into that refractory brick. Now, the actual furnace itself got its air from, again, this term comes from women's clothing, again, the bustle pipe. This encircled the furnace. These guys are inside trying to put a refractory brick lining because, again, everything here is tremendously, tremendously hot. And then from this bustle pipe, which encircles the furnace, these goosenecks hang down, and they are connected to these copper-cooled tweers, copper-made water-cooled tweers, which are basically pipes that allow the air to flow from the bustle pipe above through these goose legs and goosenecks and through these 2-year pipes into the furnace itself, and that's how the hot air gets in there. In Bethlehem, those came in at about 30 psi. That's 30 pounds per square inch. And it's actually enough to help get the material to basically float, and then the air to percolate up into it and help feed that chemical reaction that melts the iron. This is a shot of a blast furnace being lit up for the first time. You can see everything's painted, shiny, brand new, and it really didn't look that way for long. So once you had iron flowing, again, this is a long process because it's not turn it on and it instantly starts. It takes a while to actually get all the heat absorbed and then the iron to actually start melting. And you don't fill the furnace with iron immediately. You fill it with combustibles and then coke, and eventually you start trickling the iron in and you get it melting out. We can see here a overhead shot of the cast house with these runners and gates. Those direct iron to the various railroad cars underneath waiting to take it. It can also direct slag, which is the byproduct, to a different set of railroad cars. The hot metal, you can see an example of it right here. Again, we have many more photographs in our archives. And since we don't have access to them on site yet, these are just snapshots we took for research purposes early on, so we have much higher quality versions available in the future. But anyways, you can see the worker in the silver suit helping open and close these gates to direct the iron and slag to where it needs to go. And after the iron had been tapped out, this thing here called a mud gun would actually be filled with clay. It would go in and seal up the hole in the furnace, and that would keep the iron from leaking out. So it had to build up for a period of maybe 2.5 hours before it was ready to tap out again. And then to get it out, another piece called a tap hole drill. You can see the back side of it here, and you can just barely see a drill rod coming out. Would actually hammer out and drill out that clay plug that the mud gun put in there. And when this drill got to the end of that plug, molten iron would then come spewing forth out of the furnace. Here's a shot of a submarine car that will be filled with molten iron. This is a shot of it being emptied out into a foundry ladle. But these things in Bethlehem plant held 250 tons of iron at a shot. And there were multiple cars in a train. Drawings so you can see the refractory lining. Again, this wasn't just steel. There was well over a foot, and we'd have to scale it or look from our specifications about how exactly thick this lining was. It was sufficient to hold molten iron there for up to 3 days if absolutely necessary. This was a fairly reliable technology, but as usual, things could go wrong. So sometimes the train's derailed. This is the case where they call it a big hook came in and had to lift it back onto the rails. And sometimes they'd have to empty out the iron in places where it really wasn't intended to go if there was an emergency. So this is a situation where they actually poured the iron out, let it solidify, and came back in to hoist it out in some very large pieces. Other times it would trickle out onto the floor, which was very unpleasant to say the least. If this iron got into a place where there was moisture, the water underneath it would boil into steam or even disassociate between the hydrogen and oxygen and cause a massive explosion. A lot of people got injured and killed that way. That's why if you look at blast furnaces and the areas around them, you often see in steelmaking furnaces 2 brick floors because were much easier to repair than concrete, which could spall and damage, but bricks you could replace after you chip the iron away. Now this is a good time to think about that dust catching system again. We can go into a little bit more detail now that we know how the metal was handled. So you have these uptakes coming from the top of the furnace. The downcomer that does that just goes down into a dust collector. This image here shows the bottom of a collector looking up. It's a very simple device. Basically a chamber where you have the gases and the dust come in about 2/3 of the way to the top, settles down at the bottom, and then the gas gets redirected upward. Despite all the dust settling out, there's still a lot left in it, so it has to go through a secondary washing process. They have electrostatic precipitators and washers that feed water through the dust, and then eventually the water that's accumulated in this dust gets pumped into what they call a door thickener, DORR. It has a revolving rake inside of it, and these are the 2 concrete pads that are left between, I believe, C and D furnaces today. These to be steel walls that went up. They were impoundments for water. These rakes revolved around the inside and helped clarify the water. Clean water would go out the top, and then the dirty water could be discharged out the bottom with the dust inside of it. And then the vacuum filters could then clear off the dust, and then the dust could then be taken to that centering plant and recycled again. They had a saying, if you saw the sky coming red out of those furnaces, they didn't say it was pollution, they called it lost profit. Sorry, lost product, I'm sorry. This is just a chart showing the different types of iron. So these were very chemically fascinating processes. It wasn't just throw the iron ore, anthracite or coke in, and limestone and come out with molten iron. There's all sorts of different grades of iron. Like you would send it to the open hearth, you would send a different type to the Bessemer converters, yet another category for the foundries. I mean, you really had to have some very good metallurgists on board to make sure you were on top of your quality control. Now, we've been talking a lot about iron ore, but in the mid-20th century, a little bit after World War II and into the 1970s, they really started seeing that the high quality iron ore was being depleted in the United States. They started concentrating the lower grades of ore. A lot of that came from the taconite area in Minnesota. So when you concentrated this ore, you got pellets, which we call taconite pellets. So those are about 60 to 70% iron, which is pretty similar to the ore that was fed into the furnaces. So when the blast furnaces in Bethlehem were finally retired, they were relying on these taconite pellets. And that's why when you walk on the Hoover Mason trestle today, you see taconite pellets and very little actual ore, because taconite pellets were the feedstock for the furnaces at the end. And that's what blast furnaces in this country today rely upon into the modern era. So I think this is a good time to see if we have any questions. There's a lot more we can say about this, but hopefully let's walk you through the basic process and give you a peek at some of these components that were really vital in making iron making happen.
Thank you, Mike. I think one of the only questions we had so far was someone asked about the conversion to electric blast furnaces.
Maybe you mean electric arc furnaces.
I think that's probably what they're referring to, yeah.
Okay, so blast furnaces like we see here took raw materials, and blast furnaces operate in what we call integrated steel mills. That's when you take the actual materials from the ground that had to be mined, and then you combine them into and process them into an actual finished product. So what electric furnaces primarily do is take pre-existing steel and remelt it. So like if you have like an automobile that you're taking to the junkyard, it gets melted down inside an electric furnace. That steel was already made years or decades ago. And what the electric furnace does is takes it and remelts it. So it doesn't actually do the refining from the raw material, like the ore and the carbon-based coal or coke. So the electric furnace is really a recycling furnace that melts down steel that's pre-existing. And there are, of course, exceptions to everything, but by and large, most electric furnaces take pre-existing steel and remelt it. And that was one of the downfalls of the Bethlehem plant. They're making all this material from scratch, while their competitors could take steel beams from demolition sites, automobiles, you name it, and remelt that in an electric furnace, and the cost was much, much lower than going through this long, involved process with making materials from things that you mine.
Got it. Kathy had asked, when were the F&G furnaces demolished?
I believe 1965, but I should double check that.
Got it. Kendall had written in, he has a photo of one of the turbines inside of the gas blowing house. For anybody that's watching at home, we're going to have a second talk about the blowing engine house. So if anybody's curious about how the furnaces were powered, we're doing another talk on Wednesday at 2 o'clock that'll touch on that as well. Steve had asked, can you touch on how long the process takes from ore to iron at the furnace?
Well, it depends on the furnace. I want to say about 24 hours. It could be much less. It could be less than that. I really got to go through my notes and check. It's one of those things I knew years ago and just plain forgot. But yeah, it is a fairly long period because you have to descend that furnace from top to bottom, and it's not something that happens very quickly.
Got it.
That's all, I mean, this is many other reasons, of course. Why furnaces are not like an on-off proposition. When you start one, you want to run it for years. Like even the first Bethlehem iron furnace, once they got it down, there was a period where it actually went 7 years of running straight. And you could even go longer than that, depending on the furnace and your quality and your luck held out.
Interesting. I think that's all the questions that we had for today. I just want to thank Mike again for joining us, and thank everybody that at home that's watching in, and especially those who wrote in with some questions. Again, we have a lot of other programming coming up. We have a talk, like I said, at Wednesday at 2 o'clock that's going to touch on how these blast furnaces were powered. We also have a talk about John Roebling coming up, and several other talks coming up throughout the end of the month. So we encourage you to check those out here on our Facebook page or on our website at nmih.org. And also, if you're able to support the museum at this time, there's a couple different ways that you can do so, whether it's making a donation to the museum or buying a membership. Either of those will help us out a lot right now. And help us keep providing these talks for free, and also help us. We're working behind the scenes to save several important historical artifacts, so it helps us in that way too. We're doing a lot of work behind the scenes, save things. So any support that you can offer is greatly appreciated. And thanks again, Mike, for joining us this afternoon and presenting that great bit of history.
Welcome. Thank you for having me.
Have a good afternoon, everyone.